I spent over 16 hours during the school year soldering this board. Let me explain. So for a bit of context, there was a job interview this summer that I wanted to do well at, and I didn't feel like I had enough qualifications or enough experience to apply for it. To get that, I had to do something on my own. So I started a project that turned into this. I am a musician and studying electrical engineering. And so DSP, especially for audio, is an area of interest to me. So I found a microcontroller, which I'll explain more later, that is meant for like hobbyist grade DSP, and then I designed a breakout board around it. And then it turned into a little more than just a breakout board. A few things before I get too much further. I finally have an actual mic that I can use. However, I forgot to have a mic stand. So I am holding it. I have to keep my left hand about as still as possible. Otherwise there will be a lot of mic handling noise, which is terribly hard to remove in post. I also changed up the lighting setup a little bit. Let me know what you think of it. While I go over some of the design choices I made for this project, I am going to start the time lapse right here for the soldering, because that is a long time lapse. It is over 16 hours of footage and approximately 150 gigabytes of video. So the first thing that I knew when designing this board was which microcontroller it'd be based on. I have that right here. It is the Daisy Seed from Electrosmith. It is built around an STM32 of some sort for DSP, and they have a bunch of Arduino style libraries built up that you can use in VS Code to program it. They've got a bunch of examples for basic DSP, and so it's overall a very good option for getting into DSP, which is why I decided to go with it here. Additionally, it has the breadboard pins, so I can make a super simple through-hole board for it, and I can easily solder it by hand in my dorm instead of trying to deal with some QFN package or even worse, a BGA that I have no idea how to solder yet. From there, I needed to figure out some of the other things I needed the board to do. Being a guitarist, I wanted to have the ability to work this into a pedal board without too much difficulty. So I have stereo in TS as well as stereo out, and these are both mono jacks such that it is super easy to connect whatever pedal to the input and to the output, even if it is stereo. Additionally, as I've done analog signal processing before, I wanted to have a way to send and receive analog audio to and from this board. So on the sides, I have connections for external modules that will provide power as well as mono send and receive audio. And I've got that on both sides. And then I figured for symmetry, I'll do something similar on the bottom, except because I have more space to work with, I decided to make this one stereo send and receive. Now, what if I want to have digital control over it such that I can use these same potentiometers for the entire board? Well, then I need some way to send data digitally over to the external boards. Could use UART, but then I need one UART per module, which is then 3 UART controllers that I have to use. I don't even think the Daisy Seed has that. So then SPI could work. However, that needs 4 pins, which means I have to have both analog and digital routed on the same traces, which seems like a recipe for a lot of signal noise. So I ended up using I2C, which only needs 2 lines. It has serial data and serial clock. Part of the serial data command is specifying which node on the bus it is trying to communicate with. So that is why both of the jacks on the side are TRS. One is for power, one is for ground, and then one side has the analog send and receive, and the other has I2C data and clock. For the bottom, that is why only one of them is TS, the other 2 are TRS, because the one that is TS is just for the I2C bus. Additionally, you'll notice quite a few LEDs on this board. Ideally, I would have used the WS2812s from World Semi, also known as NeoPixels from Adafruit, because that only requires one serial line in order to control any number of LEDs. However, at the time of designing this, I didn't know you could get them as a through-hole component, so I had to figure out some other way to control a bunch of LEDs with very limited pins. With that, I ended up deciding to use an I/O expander. This basically takes a serial signal, in this case I'm using SPI for it, just to keep it separate from the external modules, and that is getting routed into 2 banks of 8 GPIOs, so a total of 16 per chip. Each I/O expander is right here. There's 5 of them total, giving me an extra 80 digital GPIOs. 3 of them are designated exclusively for the RGB LEDs. 1 for red, 1 for green, 1 for blue. That gives me a total of 16 RGB LEDs that I can use amongst the entire board. Some of that will be for acknowledging when signal is being transmitted over I2C. Some of that will be for signaling what these buttons do or where the potentiometers are set to. If there's MIDI running, it can signal that. Pretty much any point where there would be user interfacing, I have an LED. Additionally, most GPIOs can't provide that much current, so in order to keep the current load off of the GPIO I/O expanders, I have a transistor driver circuit set up, which allows me to only provide 1/10 of a milliamp from the GPIOs, and that will then pull about 10 milliamps through any of the RGB LED colors. If you look at the board, that is what these like triangle looking circuits are. You have the current limiting resistor right next to the LED, the transistor that will then drive it, and then another resistor that will bias the transistor to the correct operating point. In hindsight, I could have simplified this significantly and used more of the same parts for each driver. I did the calculation to get it to exactly operate in saturation. That resulted in a bill of materials that has a lot more unique parts than is required. A lot of these resistors could have been replaced with either a 10K resistor or a 1K resistor. Instead, I have like a 39K, a 360K, a 62K, and it made assembly a lot more time consuming. The other important thing to keep in mind with the design is all of the capacitors that are here. I'm not using them for RC circuits or 555 timer settings. They are almost all for decoupling or bypass. What that means is they're basically in place to help the other circuit components work with much less noise. To understand how they work, I'm going to explain a little bit of circuit theory just to make sure everyone's on the same page. So capacitors, if you've taken any introductory circuits class, are what's referred to as a short at AC. This means that if the voltage is changing, there is effectively no resistance to that voltage change coming from a capacitor. Additionally, any voltage source can be split up into 2 components, a DC offset as well as some changing component. This change can come from the wall, where you have a 60 hertz sine wave, or it can come from just noise on the circuit. By placing capacitors on the power rails, we provide a path for that changing component of the signal to go to ground instead of going into the circuit, which can affect how the circuit performs. The other way to think of this is as a battery, only for a very local region. If an integrated circuit needs more current than the board is currently providing to it, it will take a little bit of time for the board to start providing it, which means there will be a point where the voltage will sag slightly. To get around this, if you place a small and fast capacitor, usually a ceramic capacitor, super close to the voltage rail, the extra current that the circuit will need can come from the capacitor, which is much closer, so you end up with a much smaller voltage sag. Along the lines of fast-acting capacitors, most of the capacitors on this board are either ceramic or they are electrolytic. There are 2 capacitors that are neither of those on this board. They are what are referred to as tantalum capacitors. The difference between electrolytic, ceramic, and tantalum capacitors in general cases is that ceramics and tantalums are generally faster, meaning at higher frequency they have a lower effective series resistance. Basically, effective series resistance is how ideal the capacitor acts at a specific frequency depending on the geometry of the part itself. The lower the ESR is, the better. Ceramic and tantalum capacitors have a lower ESR than electrolytic capacitors. However, tantalum and electrolytic capacitors have a higher capacity per unit volume. Now, with that in mind, why wouldn't you just use tantalum capacitors for everything? Because they have a lower ESR and a higher capacity per unit volume. The reason for that, as with many things, is price. Ceramics and electrolytics are way cheaper than tantalum capacitors are. The reason I'm using tantalum capacitors here is entirely because the datasheet said so. In hindsight, I could have put an electrolytic and ceramic capacitor in parallel, and that would have worked just as well. The other challenge I faced with this design was finding a good way to switch where the audio lines were going to and coming from without needing a ton of expensive relays. Relays are basically just a switch that moves one direction to the other, leading to no signal loss along that connection. However, relays are usually a couple dollars each, and I didn't want to have to spend that much on those. To get around this, I designed a transistor-based audio switching circuit that uses a MOSFET, and that turns on a source follower amplifier that will let the audio pass through to another path without needing any extra buffering, as a source follower is basically just another buffer. There are definitely some things that I could change about this, and if you want me to go into more detail as to ways I could have improved this board, let me know. I'm happy to make that video. Eventually, once I have gone through more of this board and figured out what mistakes I made, I will make the schematic and PCB public, so you can do this if you want to as well. Beware, it is a lot of soldering. My favorite part about this board are these connections here along the sides and on the bottom. That allows for connecting many different external modules. Let me show you one of the more simple ones. So this is basically a game controller. It has a joystick here, which is just like any other game controller. Then it has another one up here. The reason for the joystick up here is because I wanted triggers or shoulder buttons. And I was thinking about how an analog trigger works, and it is basically just a potentiometer with a spring. A potentiometer with a spring is also a joystick. So I figured I can just mount a joystick at a right angle and make that work. It is a little bit flimsy. However, I can probably 3D print a bracket to keep that supported such that it doesn't wobble as much. From there, I have either a second digital joystick rotary encoder combination, or the other module is basically a D-pad with LEDs inside of the buttons. There are haptic feedback modules on these, and it is all controlled by a Raspberry Pi Pico because it is an incredibly fast microcontroller that is incredibly cheap and easy to use. If you're looking for a microcontroller to get into this, highly recommend the Raspberry Pi Picos. You can get the second version for like $5 a piece off DigiKey. As you can see here, the green and yellow lines are where the I2C bus connects, and the red is where 9-volt goes into, and black is ground, of course. Now, there's one other part of this project that is kind of insane and brings it even more over the top if it weren't over the top enough already. For a bit of context, for one of my labs this semester, we had a final project where we had to make something. Didn't really matter what, as long as it got approved by the TA. My lab partner and I thought it'd be fun to make a version of Bop It, with eventually the capability to wirelessly connect more players such that it can be like a co-op Bop It. With that, we came up with this. This is based around the LilyGo T-Display S3, which is an ESP32 based, basically Arduino with a screen on it. This particular screen is one of the touchscreen versions, but as we found out after routing the board, there are pin conflicts with the touchscreen and the GPIOs that we were using, so the touchscreen won't actually be functional. This has 2 joysticks on it in the top corners, an ABXY, as well as a D-pad on the bottom corners, and then shoulder buttons that are also potentiometers. They're push-push potentiometers, allowing for extra inputs. My favorite input, though, is this slide potentiometer that is motorized, such that you can have to fight which direction it goes, or it can show you progress through the game. Additionally, there is a DF Player Mini from DF Robot, which is a speaker and headphone amp combined with an SD card reader, such that you send it commands via UART and it plays sound. That's what the headphone jack is here for. Again, there's haptic feedback, and in theory there could be a touch screen if we disabled some of the GPIOs. In order to get all of these working from the T-Display S3 with very minimal GPIOs exposed, we had to use a significant number of muxes. However, most of the signals are analog. So we had an analog mux that would differentiate between the various signals, and then the digital signals were all put together on one line with voltage dividers to make it possible to differentiate between the various signals. So, how does this relate to the game that I started building? This is going to be the control system for the game. With the external modules, it will be possible to easily have other people connect to it and play local multiplayer, especially with the wireless from the Bop It. However, that means that all of this has to be programmed. That is going to be probably a larger task than this was, so likely the next few years, given it's been 2 videos a year. Anyway, that is all I had for this video. As always, let me know if you have questions or ideas, and also let me know what you think of the lighting setup. If you enjoyed this video, don't forget to like and subscribe, or leave a comment. It really does help me get motivation to keep making these videos. Thanks for watching, and I will see you next time.